Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Make sure to stay connected, let us know what you like, and help support our work on Patreon, so we can keep bringing you great lessons on space science. Today we are going to address a common criticism leveled at the space industry. We are often told by well-educated people how we will never visit another star system. They will insist that the technology not only does not exist, but cannot exist. In this lesson, I will discuss a technology that is not just theoretically feasible, but technologically within our grasp today. Of all the power and propulsion systems we have discussed, from chemical rockets to nuclear thermal, nuclear pulse, ion, plasma dynamic, nuclear fission, and even fusion, none of these can take us to the nearest star before we would die of old age. The math is just not on our side. And unlike opinion, math is never wrong. All my life, I have loved solving a complex equation. But that's not to say that math comes easy to me. I'm a big picture person, more innovative than attentive to detail, a bit of a dreamer. But math has always had a special place in my heart. Sort of the same way I've loved a long run, climbing a mountain, or lifting a heavy weight. Not because it wasn't hard, but because the effort itself was its own reward. I have also revered those talented at math, because unlike most other forms of inquiry, in mathematics, opinion does not matter. There is an answer, or a series of them, that is true across the universe. When math tells us something, we should listen, and the math was speaking to Paul Dirac, back in 1928. Paul, having studied the equations of relativity elucidated by Einstein, was then trying to work the equations of quantum mechanics, describing the behavior of electrons in a relativistic framework. The equations kept coming down to a square root of a variable, and as most will remember, taking the square root of a number gives two possible answers, one positive, which is intuitive, and the other negative, that we often don't consider in everyday life. It seemed ridiculous to think that these equations, describing a piece of matter like an electron, could have a negative solution, an antimatter, so to speak. But that is what the math said. And again, math does not lie. Paul published his solutions and posited the existence of this new type of matter. 4 years later, in 1932, Carl Anderson proved the existence of this form of matter by sending a hydrogen balloon far above most of the atmosphere, where high-energy cosmic ray particles, which he knew existed in space, were striking the atmosphere. Carl reasoned that these particles would have enough energy to create this elusive antimatter, including anti-electrons he called positrons. He also reasoned that these antimatter particles would not exist on Earth's surface, as they would encounter regular matter immediately after their creation, wiping themselves out in a burst of pure energy. The purest form of energy conversion is possible, in fact, with 100% of its mass becoming high-energy light, using Einstein's famous E=mc² equation, where E is the energy in joules, m is the mass in kilograms, and c is the speed of light at 2.997 times 10 to the 8th meters per second. And Maxwell's equations, where E equals hf, with h standing for Planck's constant at 6.626 times 10 to the minus 34 joule seconds, and f standing for the frequency. Using this equation, if we know the energy of any particle, we can calculate the frequency. Since the electron and positron would have the same mass, we solve for energy by saying that E equals 2 times the mass of the electron times the speed of light squared. Now that we have the energy, we can then use Maxwell's equation to solve for the frequency. Now it turns out that 2 gamma-ray photons are produced, each with an energy of 511 kiloelectron volts, which is 8.187 joules. Dividing that by Planck's constant gives us 1.236 times 10 to the 20th hertz. This matches what the particle physicists say, 1.24 exahertz. Why does all this matter to us when all we care about is getting around in space? We care about this because when we look at ways to get very massive spaceships into orbit, like this city-sized spacecraft, we have to use atomic bombs. This system could indeed use current technology to get us anywhere in the solar system very rapidly. But it would do a lot of damage to the environment, and would only be safely used far away from Earth, as it would create a lot of radioactive material and electromagnetic pulses. We know from a previous lesson that these are bad. But even this system, if built and launched from the moon's orbit, let's say, could not get us to another star in a reasonable time, because it only converts about 2% of the mass of these bombs into energy. But what if we could collect or produce antimatter, which has that 100% matter-to-energy conversion rate? It turns out that we can. Scientists used anti-electrons, positrons, with normal electrons to produce antiprotons, and then combined them with positrons to form antihydrogen at CERN. But they first did this in 1955. Now these anti-atoms only existed for 40 billionths of a second before annihilating themselves with normal matter. But by the 1990s, the scientists had been able to create an antimatter containment system, using powerful electric and magnetic energy fields to store this antihydrogen for study. A spaceship with an antimatter engine, having a mass of 100 metric tons, could accelerate at a constant velocity of 1 g, 9.81 meters per second squared, to a velocity of 95% the speed of light, 0.95 c, getting us to Alpha Centauri, a distance of 4.37 light years, in just 6 years, all the while experiencing normal Earth gravity, while we sped up halfway and then slowed down the other half. As a bonus, time dilation would make ship time only 3.6 years, conserving supplies and making a 15-year interstellar mission possible. We would only need about 4.5 tons of antimatter propellant to do this. But it took a tremendous amount of energy to produce the antimatter that we've made so far, making it relatively the most expensive material on Earth, with a relative value of quadrillions of dollars per gram, making antimatter engines technologically feasible, but practically impossible. But this may soon change. In a paper published in 2022, it was stated that positrons are difficult to create and manipulate due to their short lifetime, and their energy gain is limited by the accelerator size in conventional facilities. Alternating compact accelerator concepts in plasmas are becoming more and more mature for electrons, but positron generation and acceleration remain an outstanding challenge. Here we propose a new setup where we can generate, inject, and accelerate them in a single stage during the propagation of an intense laser beam and a plasma channel. The positrons are created from a laser-electron collision at 90 degrees, where the injection and guiding are made possible by an 800 nanocoulomb electron beam loading, which reverses the sign of the background electrostatic field. We obtain a 17 FC positron beam with giga-electron volt level central energy within 0.5 millimeters of plasma. These scientists in Portugal have been able to create particle accelerators with a maximum acceleration gradient 1,000 times more powerful than anything available before. They have found a much more efficient way to make antimatter, and with further refinement, we might be able to get this down to an affordable cost, at least affordable by space standards, But is this our only source of antimatter? It turns out that it is not. When cosmic rays strike the atmosphere, as we said before, they sometimes create antineutrons, which usually bounce away into space at high speed. Free neutrons decay in a little more than 10 minutes, as do antineutrons, turning into protons and antiprotons respectively, along with an electron and a positron. Once these now charged particles are high above the atmosphere, they get caught in the Earth's magnetic field, and the antiprotons become concentrated here, at an area of the Van Allen radiation belt called the South Atlantic Anomaly. This is where the inner ring of the Van Allen belts come closest to the Earth's surface. It's also noted to be very damaging to satellites, so most avoid it. This area of space was estimated to contain about 160 nanograms of antimatter. What if we took a satellite with a large superconducting magnet and created a magnetic field like a giant funnel, and used it to collect just 30 nanograms of this antimatter? That would allow us to get a fairly large spacecraft to Mars in just 45 days, instead of the usual 270 or so. And this source of antimatter would replace itself. If scientists can continue to refine antimatter production and storage, we will indeed become an interstellar civilization. By the way, if we ever see a gamma ray source with a frequency of about 1.24 exahertz, we'll know that one of our intergalactic neighbors has created an antimatter drive. And if it's blue shifting, and we can see it, that means they're coming to visit. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra. Hello, fellow space scholars. I wanted to thank you for being here. This channel started 4 years ago for many reasons. One of them is that I love to teach and have always wanted to learn how to create video lessons. Another was my frustration at the lack of facts in space news. I wanted to make sure that those truly interested in space science had somewhere to go to learn about the equations that make rockets possible, to give you the tools to make your own evaluations of different launch systems. But as important as understanding the equations are, they limit my channel to those with a serious interest in understanding space science. As many of you know, the YouTube algorithm promotes broad topics that are easy to understand. Our space science lessons, however, require a more detailed understanding, and I don't want to dumb the lessons down. But that makes the target audience a lot smaller. To take this channel to the next level will require that I invest more time and resources, and that will require your help. Therefore, I really need your support via Patreon or YouTube membership. Just a little bit every month can make a huge difference, and would be greatly appreciated. I thank you so much, dear friends of rocket technology, for your continued support, and I can't tell you how much it means to me. Thank you, and stay safe.
The upstream end of the alpha apparatus. The antiprotons come from the antiproton decelerator from that direction. And we trap them inside of this magnet. This is a large superconducting magnet that holds the atom trap and the charged particle trap. So we trap antiprotons and positrons in this magnet. We put them together to make antihydrogen, which is then trapped inside the atom trap. Then we shine the radiation on it, the microwaves, and cause it to escape. And when it escapes, we detect that it annihilates. You get this microscopic explosion when antimatter hits matter, and we're very good at detecting that. So that's why we're able to measure on just one atom. So what we're doing now is actually looking into antimatter for the first time, an antimatter atom. We're actually studying it the way that atomic physicists have been studying hydrogen and helium and all the other atoms in the periodic chart. We're actually addressing an antimatter atom in the same way. We're starting to learn how to do that. And that's a huge step forward for us because we've never been able to do that before. So this step of last year of storing things for 1,000 seconds, that's what allows us to do this. We need some time to interact with this trapped atom. So we demonstrated we could do that. In fact, in this experiment, we only used 240 seconds, and still we have a very strong signal that we can identify. So these things have built up. Trap antihydrogen, store it for some time, shine some light on it. In this case, it's not light, it's microwaves. Light is the next step. We'd like to shine lasers to continue the spectroscopic investigation of antimatter. That's what this is about, looking inside the structure of the anti-world. This step is very important for a few reasons. Again, we want to compare the structure of antihydrogen with that of hydrogen. That's the whole point of our physics program. So this is the first measurement of the internal structure of antihydrogen, where we've actually used radiation to see what's going on inside this antimatter atom. The other important thing about this measurement is that it demonstrates that you can actually measure with very few atoms of antimatter. If you have matter, you can just buy it. You can get your hydrogen from a gas bottle. But we have to produce these antiatoms. They're very rare. It's difficult to make them, difficult to trap them. So one of the big questions has always been, will you ever have enough to be able to make a measurement? And now we've demonstrated that even with one atom trapped at a time, on the average, we can probe the internal structure of the antihydrogen atom. So we're very excited about that. We now know that in the future we can make experiments, we can design experiments that will succeed or have a good chance of succeeding. That's a very, very important step for our community to be able to say, all right, you're actually measuring something now after more than 20 years of efforts to just learn how to get this far. So for us, it's a huge relief that we're actually starting to make measurements on antihydrogen. So what's the next step here? The idea now is we know we can measure something. The whole idea is to compare to hydrogen. And to do that, you need to measure more accurately. Okay, so in the next 5 to 10 years, what we'll be doing is improving these measurements to make them more and more precise. Hydrogen is the thing in the universe that we understand the best of all the atoms. So in order to look for a difference between hydrogen and antihydrogen, you need to be able to keep measuring more and more accurately. So that's what will happen. In fact, we're building a new machine now called Alpha 2, which will attempt to do that, both with microwaves and with lasers. So we have a double program now. In the future, the idea is just to make this measurement more precisely. Several measurements. There isn't just one that you can do. Anything we can try, we'll try. The idea is that since you can hold it for so long, you know you can measure. So that's what we're doing now.
This is the central portion of the alpha apparatus spinning into view. You're looking at the silicon annihilation detector, which is the 3 layers of segmented things. They'll peel back in a second so you can see what's inside. The tube sticking out either end is the inner portion of the cryostat, the liquid helium vessel for the magnets. Now you see the superconducting magnets that make up the atom trap. There are an octopole and 2 mirror coils. These are what actually trap the antihydrogen atoms when they're produced. They produce very strong magnetic fields that grow from the center of the apparatus. The arrows indicate the direction of the current in the superconducting magnet coils. It's about 1,000 amperes for the octopole and about 700 in each mirror coil. Now those will peel back. You'll see the vacuum chamber open up, The yellow cylinders are the electrodes for the pending trap. These are used to help trap the charged particles. The whole device sits in a superconducting magnet that gives a constant field of about 1 Tesla and holds the particles transversely to the axis. These are the potentials in red applied by the electrodes. You see a cloud of positrons in green in the center and a cloud of antiprotons that's being driven into the positron cloud to form the antihydrogen. These particles obviously have opposite charges, so they're in different curvature potentials. So now the antiprotons go into the positron cloud, hopefully very slowly so that you can make cold antihydrogen. 2 positrons scatter in the field of the antiproton and produce the antihydrogen atom. So that's it, antihydrogen, 1 antiproton with a negative charge, 1 anti-electron or positron with a positive charge. So if that antihydrogen is formed and it's slow enough, it will stay in this magnetic bathtub. You can see it at the bottom. This is the potential that's used to hold the antihydrogen atom. So if it's less than 0.5 Kelvin above absolute zero, it'll stay there. Then if we want to see if it was there, we release it quickly. That's what's happened here. We've turned off the magnets. The antiproton from the antihydrogen annihilates, produces high-energy charged particles which come out and are registered by the silicon detector. So we can recreate the position at which the thing annihilated. That's how you know you had antihydrogen. Now here's the experiment we've just done. The antihydrogen is trapped because it's slightly magnetic, and that's indicated by the little arrow flying around with the atom. We shine microwaves on that little magnet and cause it to flip into the other direction. It'll happen more slowly here. You see the magnetic moment, sort of like a compass needle in the antihydrogen atom, has to point in one direction for it to be trapped. The microwave radiation flips that magnetic direction, and that means that the atom is untrapped and comes out. And that's what happens. You detect the annihilation. You need to have the frequencies of the microwaves exactly correct. And that's what's resonant about this experiment. So if you tune it correctly, you force the antihydrogen to come out, and you can detect it. That's how you know you've done a resonant interaction.